We are Group 3, Tom Anderson, Mary Costello, Tom Hoban, Steve Magner, and Rich Shoemaker, presenting our term project, a case study, security analytics for ACME Automotive. We will present a plan to secure our autonomous vehicle using a data-driven approach to network security. Even though autonomous vehicles may be years away, the time to be designing cybersecurity into autonomous vehicles is now. Mary Costello will present the vehicle network architecture. Steve Magner will present the types of messages present on the vehicle's network. Tom Hoban will present potential threats to the vehicle. Rich Shoemaker will present analytic tools available for data-driven network security, and Tom Anderson will merge the topics of vehicle networks and security analytic tools to show how security analytics can be applied to vehicles to mitigate potential threats. I'm Mary Costello, a cybersecurity engineer here at ACME Automotive, and I work in vehicle and mobility cybersecurity on the research team. And I'll be presenting to you the network architecture of current vehicles and propose a configuration for our vehicles of the future. Marketing is advertising the vision of autonomous vehicles, and it goes something like this. You use an app on your phone to schedule a car to pick you up at your house to take you to a meeting where you're presenting the AV plan to the board of directors. The car arrives at your house at promptly at 8 a.m. with the best route to the office. As the vehicle drives you to your destination, you connect your laptop to the Wi-Fi and put the finishing touches on your presentation and send it to a coworker. The vehicle gets the message there's an accident along the route, so it determines a new route to avoid the accident. Since your presentation is finished, you decide to watch the end of the movie you missed last night because you dozed off. In the meantime, your coworker has received the presentation and has questions. He decides to FaceTime you to ask you the questions. So up pops your coworker in the middle of your movie. You have a quick conversation to take care of the issues, all the while the vehicle is driving you to your destination. Once you arrive at your destination, the vehicle will park itself. You go into the building, do your presentation, and when you step out of the building, the vehicle is waiting for you at the curb. It takes you back home while you review the email from your boss about the presentation. You may be wondering, how does all this autonomous vehicle magic happen, and why does a vehicle need to be cyber secure? Well, I'm going to attempt to answer these questions by describing the vehicle network architecture. The vehicle network architecture looks a little like this diagram. There are two main parts to the vehicle network. The top portion shows the external communications where the vehicle is communicating with all sorts of outside entities. The lower portion shows the internal network of the electronic control units, or ECUs, that perform the operation of the vehicle. The two networks work hand in hand, sending and receiving messages. All these communication points are no different than the connection points of servers and laptops on an enterprise network and are open to the attack in the same way. The difference here is vehicles are moving, and a malicious attack can have fatal results if the vehicle doesn't operate as it should. So let's take a closer look at the in-vehicle network. The in-vehicle network is what allows the ECUs to communicate with each other to operate the vehicle. They receive network messages containing data to perform operations. There are three main communication protocols in today's vehicles: Ethernet, Control Area Network, or CAN, and Local Internal Network, or LIN. The Ethernet protocol is new to vehicles and was introduced for the high-speed bandwidth of approximately 70 megabytes per second necessary for cameras and sensors. The CAN protocol is used for safety-critical system modules such as anti-lock brakes and engine control. This protocol is the original protocol used in vehicles. It is not very secure. It has low bandwidth of just 1 megabyte per second and nanosecond latency or response time, which is necessary for the safety-critical systems it controls. LIN is an open source protocol that runs the less critical ECUs such as door locks, seat controls, and makes cellular connections for the infotainment system. This diagram shows the vehicle network of tomorrow. The concept is similar. There's a wired in-vehicle network and an external wireless Internet of Vehicle network. To support a Level 5 autonomous vehicle, and that's a completely automated driverless vehicle, sensors play a key role in the operation of the vehicle. We propose putting an Ethernet backbone in the vehicle, allowing for high-speed bandwidth, and also serves as a secure entry point to safety-critical messages. These safety-critical messages will travel on an upgraded, more secure control area network with flexible data rate, or CAN-FD, which is more secure and can handle 64-bit payload instead of just the 8-bit payload of today. The automotive Ethernet currently being developed has a starting base rate of 100 millibytes per second instead of just 70 millibytes per second of today. So this will allow the support of the sensors for the autonomous vehicle. So back to the question of how does all this autonomous vehicle magic happen and why is cybersecurity important? The answer is through sensors and large amounts of data. Because the large amounts of data being transmitted through many connections, security measures need to be applied to ensure the safety of the vehicles. So Steve is going to talk next, and he's going to talk about the types of messages transmitted on the vehicle network.
Hi, my name is Steve Magnier, and today I will be talking about the types of messages and data that we would expect to see on the vehicle network. Vehicle to infrastructure, or V2I communication, is an essential part of intelligent transportation systems, or ITS. V2I communication consists of a bidirectional exchange of information between the vehicle and the road infrastructure. This information includes vehicle-generated traffic data gathered from other vehicles, data from sensors installed in the road infrastructure, for example, cameras, road signs, street lights, traffic lights, lane markers, parking meters, etc., and data broadcasted from the ITS, for example, speed limits, weather conditions, accidents, etc. This information exchange is done wirelessly by means of the cellular network and or a dedicated short-range communication, or DSRC, frequencies. In the ITS, V2I sensors can acquire infrastructural data and provide travelers with real-time advice, sending information on road conditions, traffic congestion, accidents in the roadway, presence of construction sites, and even the availability of parking spaces. Likewise, traffic supervision and management systems can use the data collected from the infrastructure and vehicles to set variable speed limits and adjust the signal phase and timing, or SPAT, to achieve fuel savings and facilitate traffic flows. Vehicle-to-vehicle communication enables vehicles to exchange data in real time. This information exchange is done wirelessly via dedicated short-range communication, DSRC, frequencies, the same used in V2I communications. Thanks to V2V, vehicles can share their speed, location, and heading, as well as any other relevant information, giving the system a 360-degree representation of its surroundings. The main goal of V2V communication is to avoid accidents by allowing vehicles in transit to send that relevant speed and position data to one another over an ad hoc mesh network. This specific network is called VANET, meaning Vehicular Ad Hoc Networks. VANET also consists of a wireless network whereby vehicles can communicate with one another and share the same relevant information about their driving behaviors, as mentioned earlier. Since the V2V communications were conceived as a mesh network, each vehicle becomes a node that can capture, send, and retransmit signals. The importance of this technology is to prove the safety of the roads by providing incident alerts before a driver sees or detects them. Vehicle-to-cloud communication allows the vehicle the ability to deliver services from the car manufacturer as well as from other providers automatically over the internet. Connected vehicles constantly interact with the cloud ecosystem using broadband cellular mobile networks, specifically LTE, which stands for long term evolution. The connected cars are served by multiple services. The communication happens over Ethernet with different TCP, UDP, HTTP based protocols. The services on the cloud provide specific data to the connected vehicle. This data corresponds to the various aspects like vehicle information, positioning data, analytics data, or data needed for the autonomous vehicle movement. Additional services include multimedia, phone connectivity, and over-the-air updates. The main benefit is the ability to completely change the configuration and functionality of the car without significant physical changes to the vehicle. Each automobile regularly calls quote unquote home to the cloud, providing engineers with extensive information regarding the performance of each car. In most cases, engineers can fix any issues with the car without any involvement from the driver. Further, this process allows us to listen to our customers and decide what features we should add. Since the entire vehicle is managed by software from the cloud, it is possible to complete the development and testing in order to easily deliver upgrades. All data to and from the cloud is encrypted. A VPN is established directly to the car, and all software packages are signed and verified. Vehicle to pedestrian, or V2P, communication exists to avoid accidents. Typically, V2P crash prevention systems involve periodic exchange of safety messages among vehicles and vulnerable road users, or VRUs. This communication can happen either directly using ad hoc communication technologies such as IEEE 802.11p, or indirectly using infrastructure-based communication such as cellular technology. V2P communication performs its operations in three phases: detection, tracking and trajectory prediction, and action. A typical safety message may contain speed, location, and direction of the respective vehicle or VRU. This information may then be used for the detection, tracking, and trajectory prediction phases by the recipients of the safety message. Vehicles transmit at a rate of approximately 10 safety messages per second. VRUs may transmit safety messages with varying frequency. This frequency may depend on various parameters, such as their location and speed. Vehicle to everything, or V2X communication, is the umbrella term for a vehicle's communication system. V2X consists of all the types of communications discussed prior, specifically vehicle to infrastructure, vehicle to vehicle, vehicle to cloud, and vehicle to pedestrian communications. Most commonly, these technologies either use messages based on IEEE 802.11p standard or long-term evolution, otherwise known as LTE-based technology. As mentioned earlier, the standard for V2X communication is DSRC, Dedicated Short Range Communication. The basic safety message, or BSM, on DSRC conveys state information about the transmitting vehicle. The BSM is a two-part message. The first part is periodic, sent every 10 seconds, and the second part is event-driven. For securing V2X communications, the common approach is to use asymmetric cryptography using a public key infrastructure, or PKI, for the management of security credentials. PKI enables secure exchange of messages over the network. Each vehicle is provided an asymmetric key pair and a certificate. This ensures integrity and authenticity. The certificate contains the public key with V2X specific attributes and is signed by the key issuing authority. With the emergence of V2X technology and connected cars in general, V2X applications and protocols will be an ever-increasing target for malicious actors. Next, Tom Hoban will discuss the potential threats to connected vehicles.
My name is Tom Hoban. I'm a cybersecurity engineer who will be reviewing potential threats to a connected vehicle.
We'll start with more broad attacks that indirectly have an effect and can act as potential threats to connected vehicles. Connected vehicles are reliant on an active source of electricity, and that there are components within the car that run on electricity, which assist in the car's basic functions, as well as electric powered components that are used to transmit data and communicate with external entities. The threat of power grid disruption is growing twofold, especially in the United States. Nation state and state like actors have begun to realize that it's very common for security mechanisms put into place to protect components of the national power grid are poor at best, if there are any at all, making them an easy target for attacks. In addition to deliberate attacks, the combination of aging infrastructure and increasing demand for power also runs the risk of there being a failure resulting in a loss of electricity. While power grid disruption may not be a threat deliberately focused at connected cars, the amplified nature of such a disruption would certainly have its effect on connected cars.
As we get closer to directly targeted attacks and threats to connected vehicles, it is important that we discuss vehicle signal transmission interruption. Driverless vehicles are designed to collect the same kinds of information that a human driver would, but they are malicious individuals who could potentially cause a connected vehicle to do something the driver did not intend, resulting in outcomes that are as severe as death by carrying out a vehicle sensor attack, for example. Vehicle transmission interruptions can be caused by a number of acts of malfeasance. Chiefly, though, GPS jamming and spoofing must be considered a primary concern pertaining to transmission interruption. GPS signal spoofing is not hard to carry out, and more time must be spent by companies and academics alike to find better mechanisms for spoofing defense. Human safety with connected vehicles must be the absolute number one priority. Ensuring that jamming a connected vehicle safety systems, such as radar and LiDAR, is extremely difficult, if not impossible, must be made an absolute priority. Distributed denial of service attacks on connected vehicles are a very real threat, with the intent being an ITS fails to respond to its requests. These types of distributed denial of service attacks can be carried out by using compromised intelligent transportation systems. Motivation for carrying out such an attack could be any number of reasons, but with DDoS attacks related to connected vehicles, the motivation would likely stem from one of political, emotional, ideological, or exploitative motives. With non-vehicle type assets, DDoS attacks typically amount to not much more than wasted time, mild annoyance, and possibly lost revenue. The component of a human being in one of these connected vehicles ups to the degree of tolerance for such an attack to be basically zero. Given the frequency of such threats being acted upon, DDoS attacks are something to be taken very seriously.
Hi, I'm Rick Shoemaker, and I'm going to be talking about analytic tools to secure the network. In the past few years, we have seen an explosion in devices that are now a part of the Internet of Things, and automobiles are certainly part of that. It's predicted by 2023, there could be roughly 53% of the Internet of Things will be automobiles, either fleet vehicles, personal vehicles, you name it. So there's the concern around that type of big data that's being generated by all of those devices or automobiles and their devices attached to them, be it the car-to-car communication, the diagnostics those automobiles are actively taking in and then transmitting up to a central location from a third-party application or from the manufacturer, potentially to a dealership. So it's the concern of how much data is being generated, how is the privacy handled around that data, and who is keeping up with that data? How does the consumer know about this data and where it's going and what it's doing? So big data in automobiles. We've now gone from automobile as a way to get from point A to point B to a sort of an entertainment vessel while we go from point A to point B. And cars are now part of a source collection and a goal of the data that is collected. And what's the goal of that? So it could be the sensors in a car telling you diagnostic information on the functioning parts of the car, or if it's malfunctioning, it could be good for reporting back to dealerships, with reminders on service bulletins or service intervals that you need to come and get your car taken care of. It could be the telemetry in cars, talk about GPS and the tracking for fleet management, that sort of thing. Then there's user devices that are connected in our vehicles, and those now are more and more apps being integrated, from GPS to music to rideshare apps, you name it, social media. So the cars are now a big data generator in and of themselves. So, a concern is coming down to, when it comes to analyzing the data that's coming from these cars, how protected is it? Who owns that data? Where's that data at? And is it being used for any, surveillance possibly? Is that accessible to, out third parties who might purchase this data, or government tracking, that sort of thing? So it's a lot around automobiles and data that I don't think is really getting the attention that it needs to. And we need to start talking about it more. So we're now getting to the analytics. We talked about big data. We talked about all the things, the data that we're generating. What about the analytics side? How about the security that is deployed around that data? And turns out there's a lot of vulnerabilities and quality control issues from manufacturers that, in the rush to get these automobiles on the road, get through the production cycle, they're sending them out there with a lot of untested software and a lot of untested security loopholes that they don't recognize until it's been made known that there's a compromise. I personally own a 2015 Jeep Grand Cherokee that was famous several years ago for some white hat hackers who found a way to remotely access that exact vehicle, and the manufacturer sent me the notice to come and immediately get my car updated, or I could do it myself. And I actually did do the over-the-air update to my car, which was a really strange feeling to sit there and get a USB stick, put a software package on there, go to my car, plug it into my USB in my car, and sit there and wait while it communicated with the manufacturer network via satellite, and then update my car. So these are things like this that I am surprised and shocked in some of my research, that there's so little finished testing being done on these software that runs our vehicles. And so also in coming upon these different third-party analytic applications like RapidMiner, Board, Automated Metrics. OnStar is one it's popular with General Motors. And upon reading about it, I've had OnStar on my Chevrolet vehicles before, and it's a great tool, and I always thought it was just for GPS and emergencies. But reading about it now, it has evolved into many things, to your diagnostics, to remotely unlocking your car if you forgot your key, or if you somehow locked your key in your car. And so with that kind of capability, I was never informed of any kind of data that Chevrolet may have been gathering about my vehicle. So, and the same thing for my Jeep. I don't, unless there was some sort of EULA that I just kind of looked over. There's nothing that is coming out and saying, "Hey, you're all this data, and your life is being recorded and we're going to do what we are, whatever they're going to do with it. I don't even know. So I'm really curious about more analytics being done on this type of data and what's being generated. And that's a very gray area. And I'm very concerned about it. I think there should be more concerned about this. So, and speaking earlier on security flaws, possible potential vulnerabilities in the software going into our cars, again, asking the question, who owns this data exactly? Do we, the consumer, own this? Is it all owned by the manufacturer? Do third-party application manufacturers, do they own this data now? So the concern I have is, if you're getting this data and you're gathering these analytics, there should be more consumer notification on this type of data and how you're analyzing things that my car is doing, or by extension, what I'm doing when I am traveling and going about my life. And what is the point at which it becomes a major problem that the manufacturers are allowing cars to go out that are vulnerable to either flaws in the function of the car or possible flaws in allowing somebody to gain access to the car. We're going more to these electronic vehicles and self-driving. There doesn't seem to be enough discussion about how to properly secure this data and how to analyze the data in a secure and private way and is transparent to the consumer. I think that's a big problem. The big situation is the transparency of the analytics and the consumer.
Hi, I'm Tom Anderson, a cybersecurity engineer at ACME Automotive Corp. I head up the prevention and mitigation team, and I'm going to present to you our plan to deal with cybersecurity threats and vulnerabilities in ACME autonomous vehicles and their codependent communication networks. Our prevention and mitigation plans can be broken up into proactive security and reactive security. Proactive security involves creating all of the cybersecurity infrastructure needed to prevent, frustrate, and detect any intrusions or malfunctions which may result in a loss of vehicle or network integrity, availability, or confidentiality. This infrastructure includes a defense in-depth approach utilizing redundant, co-witnessing vehicle sensors, layered onboard threat management, network segmentation, public key and decentralized encryption systems, a trust sharing system, and a hybrid intrusion detection system. Reactive security involves responding to actual events to resolve issues of conflicting information, anomalous behavior, or triggering of attack signature alarms. These are the processes involved in utilizing and putting into practice our proactive infrastructure. These include sorting or rejecting low trust information to eliminate possible malicious communications, using anomaly detection to poll other vehicles, centralized IDS, and vehicle occupants for verification and clarification, sharing information with neighboring vehicles and using shared information to make decisions and block hosts, and ultimately falling back to the most trusted sources of information and commands, including giving over manual vehicular control or safely removing the vehicle from the road for further diagnostics and instructions. The security infrastructure of a vehicular network begins at the individual vehicle, which is tasked with protecting its occupants and everyone around it. In order to guarantee the availability of accurate information about the road, other vehicles, and potential obstacles, onboard sensors should have redundancy, both for fallback in case of malfunction and to co-witness events for mutual verification of readings. Hardware must be physically tamper-proof with self-diagnostics to determine if anything's out of spec. Sensors should self-calibrate through mutual verification with co-witnessing sensors. Software must also be tamper-proof, with updates cryptographically authenticated from an official manufacturer software mirror. Vehicles should also create a profile of its users and typical trips in order to create a baseline against which to detect anomalous behavior that may indicate that the vehicle is being stolen or controlled maliciously. Anomalous behavior beyond a given threshold would need to be verified via cryptographic authentication. The base security assumption is that any and all information received from any onboard system or remote source may be compromised in some way, whether by mechanical failure, communication interruption, or malicious actor. Every value received is verified against an onboard co-witnessing sensor or a neighboring vehicle or roadside sensor or other resource such as GPS. Although vehicles should employ the principle of cautionary acceptance and erring on the side of safety when it comes to unverified indications of pedestrians or other potentially lethal collisions, verification is otherwise necessary. Trust is established by a history of accurate and verified information provided by a given source. Onboard systems are not necessarily the most trusted. For example, your vehicle may have an old, outdated, or flaky sensor that provides low-resolution, intermittent, or imprecise information, whereas your neighbor Bob has a brand new luxury SUV with state-of-the-art sensors. So if you and Bob are driving side by side, it would be prudent to trust Bob's sensors reading of the same event over your own. Machine learning algorithms are used to sort through various sources of information about the same environmental conditions, resolve discrepancies, and prioritize and merge the best information for making a decision. Moreover, vehicles and other nodes in the network may all share their trust ratings such that everyone can be aware of the best possible information at any given place and any given time. Cryptography forms the basis of the information trust infrastructure through authentication of communicators, ensuring the integrity and non-repudiation of messages received, and protecting the confidentiality of communications. Because cryptography is so vital to ensuring trusted information is being acted upon, the infrastructure must be durable even when some pieces are malfunctioning or unavailable. For that reason, we're proposing to use trusted centralized certificate authorities to authenticate keys when the internet is accessible to perform those lookups, but because traffic will still be flowing even during network disruptions, such as DDoS attacks, vehicles should maintain a local keyring of trusted keys and communicate them over the local vehicular ad hoc network. Each vehicle may have a keyring containing potentially hundreds of public keys for vehicles, traffic sensors, fog nodes, and other hosts within the passenger's hometown, route of commute, or other frequently visited areas. This establishes a web of trust through which other keys may be requested as well. Because vehicles must act upon information in real time with minimal latency, they should implement a lightweight symmetric block cipher in hardware, which conforms to the New European Schemes for Signatures, Integrity, and Encryption, or NESI standard. This includes AES Rheindahl, MISTI 1, Camellia, or TripleDES. To identify and protect against malicious actors, we will implement a hybrid, centralized, and distributed intrusion detection system. The centralized element will engage a powerful deep learning neural network. Using data collected from the edge nodes, it will identify zero-day attacks and advanced persistent threats, and generate an attack signature database and blacklist. The distributed elements will exist at the edge nodes, with non-processor intensive attack signature analysis and firewalls to block blacklisted hosts. Besides downloading the centrally generated blacklist, each vehicle, traffic signal, sensor, or other node can add hosts to the blacklist based on criteria such as matching an attack signature or providing information contrary to the preponderance of well-trusted nodes. Furthermore, the network can engage honeypots to mimic vehicles and other nodes in order to detect and collect data about malicious actors to feed the centralized IDS and also promulgate new blacklist entries. Each of these distributed nodes may share their blacklists amongst each other without needing to communicate with the centralized IDS, but will also periodically provide data to feed the deep learning algorithm. In conclusion, autonomous vehicles are complex and vulnerable to many possible avenues for accidental or malicious errors to enter into their calculations, which could cost lives and property damage. To mitigate these risks, we will assume a posture of skepticism about all data and then use a system of trust building and verification to gain confidence in the information before it is acted upon. We will maintain the integrity and confidentiality of the network and information transmitted over it using redundant methods of cryptography. And we will employ a defense-in-depth approach to detecting and expunging malicious actors. All the while, we will not assume that the entire network is accessible or functional, but each piece down to a single vehicle or group of vehicles can still operate independently and execute on this mitigation plan in at least a limited aspect. This will ensure the durability and practicality of depending on our autonomous vehicles regardless of adversities.